Alright guys, so this is the lecture video for lesson, I believe 3. It talks about finding 3D force resultants using the unit vector, which is slightly different than the way that we used it, um, the way that we found resultant forces in the past, because we were able to break up the force into just two components and solve that way. This is a little bit different because you're looking at it differently, but I'm trying to show you in this video that it means essentially the same thing. So so basically this first part here is explaining the two different ways that forces can be described, right? So because they're vectors, they always have to have a magnitude, units, direction, and point of application. So the magnitude just means that there's some description of the strength of the force. The units are entirely, like their purpose is to contextualize that strength, right? Because, for example, 1 pound of force is different than 1 newton of force, right? So you can't just say 1 for your magnitude without any units, because that's essentially useless. Similarly, the direction gives context to how that force is applied, right? Because if I'm pushing up on something, it'll act differently than if I'm pushing left on something. And then finally, the point of application, which is not always relevant in the answer. So kind of think about that a little bit. But the point of application is important when you're looking at a situation where the context of where you push on the force makes a difference. So there's two different ways to kind of describe all this information. In lesson 2, we described it this way, where it was some number, some units acting some direction at point whatever, right? And that's usually only really helpful in a 2D situation, because down, left, up, right implies that it's acting in one plane, right? Which is a two-dimensional situation. The other way to write it is in this example here, the second example, where it's written in terms of a vector and component notation already. So essentially, think about it this way. These numbers in this bracket describe the magnitude and the direction in this form already. So this number here is the magnitude of the force acting in the x direction. This is the magnitude of the force acting in the y direction, and this is the magnitude of the force acting in the z direction. So you have an inherent magnitude and an inherent direction built into this format already. So because of that, and then you have your units and your point of application. But because of that, it's easiest to look at stuff in 3D in this way. And that's kind of what I want to go over in this video, is that the procedure is a little different just because of how the final answer is going to look. So that's kind of what I'm going into now. I added step 0 here because I think it's easier and it eliminates you doing a bunch of steps at once. But step 0 is essentially writing out all of the coordinates for the points that you're looking at. So if you have like a rectangular prism here, which is an example we did in class, you have a bunch of points that could have forces acting through them, right? Which means you have to consider the coordinates for that point versus the coordinates for this one. And if I have a force going from here, from this one down here to this coordinate up here, that's a lot to do in my head to define that position vector. So my recommendation would be is to write out the coordinates for these 2 points separately so that that's its own step and you don't have to juggle that in the next step. So that's step 0. Step 1 is to find the position vector, right? So basically define the direction of the force itself. So the force will start at some point and it will travel to another one, right? When you describe how you're going somewhere, you say I'm going from my house to Publix, right? In vectors, when you're finding the position vector, you essentially have to start with the information for the endpoint coordinate, So you have your x components, your y components, and your z components, but essentially you're subtracting the two of them from each other. So you're subtracting the x component of the final point minus the x component of the initial point. Same thing with the y and the z. This will get you your position vector. And it's important to note that at this point, you still have a vector, right? But if I'm describing the position of Publix relative to my house, that still has an inherent magnitude in it, right? It'll be 3 miles or something like that. So the importance of that is if I'm applying a force in some direction, by multiplying the magnitude of the force that I know I'm applying through a position vector that has an inherent magnitude already, I'm going to end up scaling up the components of that force vector. So essentially what I have to do is I have to make this vector here that we just found have a magnitude of 1, so that when I multiply something through it, I don't scale it up. So how do you make a number or a value 1? It's by dividing it by its own magnitude. So by finding the magnitude of that vector, which is just by using the distance formula, which is this one right here, you can end up finding the number that you have to divide by, right? So this here is the distance formula, but essentially it's just the square root of the sum of all of the components that you just found up here, right? So essentially by doing that, you're going to get a number, right? Because these are all independent numbers here, and then you're just squaring them, adding them, and square rooting them. So your final answer for R, the magnitude of R, is going to be a number. That's that 3 miles I was talking about. So by finding the magnitude and knowing the position vector, you can find the unit vector, which in the video you know is a unitless vector with a magnitude of 1. And that's important because the magnitude won't scale up the number that you find for your force vector. And the unitless portion of it means that if I multiply a force with a magnitude of 3 newtons, I won't end up with a value of Newton meters. Because remember, the vector we found originally up here, the position vector describes the position in terms of the units that were used for that position. So that's important. So the unit vector is essentially you take the components of each of the directions that you had in your position vector. So you take just the x component that you had, and then you divide it by the magnitude that you found in step 2. And then you do the same thing for the y position and the z position. So you divide all 3 components by the entire magnitude. And then if you really wanted to verify that that had a magnitude of 1, what you could do is you could say, all right, these are my new components, right? I'm going to plug those 3 values into this equation so that I should be able to get a number that equals 1. So that's if you want to verify that. From there, that value calculates this number right here. So now you have a vector again. So you went from a vector, the magnitude of that vector is then a number, and then by dividing a vector by that number, you still end up with a vector. So now this describes the direction of the force being applied. So it describes the direction of this arrow right here without having a magnitude that will be affecting or affected by the force that I'm applying, that I know that I'm applying. So essentially, if I'm pushing a box in the direction of Publix, right, across my living room floor, and I know I'm pushing that box 3 meters or 3 pounds, if I'm applying 3 pounds of force to that box, by multiplying it into a vector that is inherently 3 miles in magnitude, I'm scaling up that by a lot. So this vector now has a magnitude of 1, so the overall resulting force vector that I get won't be impacted by that. This value here is usually given in the problem. It'll usually say that something is pushing or pulling or acting in some direction at with 10 pounds of force from point A to point B, right? And you just got rid of the point A to point B part by doing this, but then you have to consider the 10 pounds part because there is a value of that force, right? And that is this here. So you multiply this number. So this here is a number, oh no. This magnitude of F here is the number given in the problem, multiplied into the vector with a magnitude of 1 will then get you a vector which is denoted as F with an arrow over it because it's a force vector. But it'll get you a vector with the appropriate magnitude in the appropriate direction. So now you have this component here and this component here. You just have to remember your units. And in the case of resultant forces, it always acts at the center of mass of the object. So I'm sorry, that's incorrect. It acts at the common point. So the resultant force of this cube or this prism up here would have to be the combination of certain forces acting in the acting through or at a common point. So essentially I just drew 3 arrows here. So I have this one going from A to B. I need to make this bigger. I have this one going from A to B, and then I have another one going across this bottom face, and then I have another one going across the diagonal. So all of those go through A. So because of that, your point of application of this force would be through A. So that is 3D forces and essentially the steps that you have to go through to find the resultant force in 3 dimensions using the unit vector.